Good afternoon and welcome, everyone. My name is Sierra Lumonico, and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the Program Lead for the Skule Lunch and Learn. I would like to thank all of you for tuning in for today's event. We have alumni joining in from all over the world, guests from 15 different countries, including Canada, the Dominican Republic, Germany, Hong Kong, India, Iran, Israel, Italy, Jamaica, Mexico, the Netherlands, Pakistan, the United Kingdom, the United States, and Uruguay. Now, before we start today's presentation, I wish to acknowledge the land in which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have the opportunity to work on this land. Now, I hope everyone is excited about today's presentation, as our guest speaker is a pioneer in metal additive manufacturing, 3D printing, revolutionizing industries with the ability to create complex parts with precision and flexibility. Now, Professor Yu Zou research aligns with U of T's Defy Gravity campaign, particularly in creating a sustainable future and driving scientific discovery. His work explores how metal 3D printing can reduce waste, accelerate production, and create customized designs in critical industries like aerospace, healthcare, and engineering, offering transformative solutions for both sustainability and innovation. Now, a quick housekeeping item. At the end of today's event, we will have time for a formal Q&A session. Should you have questions for the professor, please submit them using the Q&A button below on your bottom of your screen. For the individuals who submitted questions during the registration period, thank you. Thank you for pursuing your curiosities and sharing your insightful questions with us. Now, it's my pleasure to introduce a true cornerstone of our community, our remarkable MC and the unwavering heartbeat of the Skule Lunch Learn program, Laurie Hevola. Laurie isn't just an electrical engineering 65 graduate. He's a trailblazer within the U of T community. For over a decade, he's poured his energy, insight, and passion into leading the Skule Lunch Learn program, creating a space where innovation thrives and ideas flourish. Laurie's dedication ensures that while the program evolves, it remains rooted in tradition that make it so meaningful to all of us here today. And with that, please join me in welcoming Laurie Hevola, who will now introduce our today's speaker for today's event. Thank you.
Thank you, Sarah, for your very warm introduction. It is indeed my pleasure to welcome our guest speaker today, Professor Yu Zou, who will discuss how metal additive manufacturing is transforming industries and driving the future of healthcare and sustainability. Dr. Zou is an associate professor in the Department of Materials Science and Engineering here at U of T, holds the Canada Research Chair, and is the Dean's Spark Professor. With advanced degrees from Beihang University, McGill University, and the Federal Institute of Technology, otherwise known as ETH in Zurich, Switzerland, and postdoctoral work at the Massachusetts Institute of Technology, his research focuses on materials with extreme properties. He leads the Laboratory for Extreme Mechanics and Additive Manufacturing, where research topics include the design of novel metallic materials, multi-scale mechanical testing, metal additive manufacturing, and applied machine learning. Courses that he teaches include mechanical behavior of materials, fracture and failure of materials, and additive manufacturing of advanced engineering materials. And now, without further ado, please join me in welcoming our guest speaker, Professor Yu Zou.
Thank you, Laurie, for the kind introduction. Thank you for inviting me for this great event. And today I'm going to talk about metal additive manufacturing, sometimes called metal 3D printing. I'm going to talk about like the fundamentals about 3D printing to real industry applications. This is not a research seminar, but mainly about the fundamental knowledge and education session. Okay, so first, so I want to talk about the outline of my presentation. I'm going to give a brief introduction about my background and also introduce my additive manufacturing course at U of T and talk about a brief history and the current status of AM. And then I'm going to talk about what's the applications of AM technique for industry. And then I'm going to give an overview about the additive manufacturing technique and then talk about the recent research project in my lab and then share some outlook on metal AM. There's quite a lot of things I want to talk about. I hope I can include something useful for the broader range of audience. Okay, first, so I want to briefly introduce about myself. The material science engineering degree in training, mainly on physical metals and alloys. And then from my postdoc, I did a postdoc focused on laser-based additive manufacturing. I joined the U of T in 2018 and built up a lab mainly focused on metals and alloy mechanics and manufacturing. In our lab, we work on 4 research themes: materials design mainly focus on metals and alloy, mechanical behavior of the materials manufacturing. That's the main topic today. Covers laser-based additive manufacturing and the solid-state additive manufacturing like cold spray. Also, we work on machine learning for alloy design and computer vision for advanced manufacturing. Over the past few years, we got funding support from various government agencies, federal government and the Ontario government. And also we collaborate with many government labs. Also, we work closely with industry partners. Okay, so let me talk about the additive manufacturing course in our department. Additive advanced manufacturing is a strategic direction in our department. In 2021, I designed a new course titled Advanced Manufacturing of Additive Manufacturing of Advanced Engineering Material, focused on 3D printing of metals and alloy for structural applications. And then this course has been shared in a few social media and caught a lot of attention. So in this course is a intensive course. And in the morning sessions, I give lectures on the fundamental knowledge about the additive manufacturing. And then in the afternoon, the student have a group project and discussion. They have the opportunity to do hands-on projects. And then toward the end of the course, the student have the opportunity to give a presentation to share what they achieved in this course. Over the past few years, about 200 students have taken this course. We got quite feedback from the students about this course. Particularly this year, we got a chance to visit industry, our industry partner, the student had the opportunity to see what's real going on in the real industry. So we first visited a company called Burlock Technologies in Ontario, and the student got a chance to see different additive manufacturing equipment, got a chance to talk to the center there, and also we even built up a research collaboration. And then the second company we visit is Skule Engineering, which is a leading company in die casting, and then we learn how they use additive manufacturing technique for in the die casting process. And then last we visit Magna International, and then we learn how they use a laser cladding system to fabricate the two parts and for the automobile industry. The student get opportunity to talk to researchers, engineers in the industry, and bridge the gaps between what they learn in the course and the real industry applications. Okay, so now I'm trying to use the next half an hour to give a quick introduction about the additive manufacturing technique and where people can use the additive manufacturing. So first, so want to briefly talk about the term called 3D printing. I think most of the audience are very familiar with 2D print and 3D print. So basically, 3D printing process involve 8 stages. And first, we create a CAD file, and then we transfer it to STL file, and then how the file transfer to the machine, and set up the machine with the printing parameter, and then you build up your parts, and then you remove the supporting structure, and how the post-processing process, and then for the final applications. So the 3D printing process is based on the concept of the material is added together or fused together layer by layer. So I think most of people are familiar with the concept and the procedure about the 3D printing. Now people may wonder, sometimes we use the term 3D printing, sometimes we use the term of additive manufacturing. What's the difference between them? So basically, there's not a big difference between these two terms, and additive manufacturing is a formalized term for what to use because of a rapid prototyping, or right now is popular called 3D printing. But 3D printing is generally used for to describe the kind of entry level printing process, like printing polymers. So you can see in the image on the right is a FDM process, and we normally call this polymer 3D printing. For AM, additive manufacturing is typically used to describe the advanced or more precise techniques. For example, most for metal ceramics. For example, a technique we showed here called selective laser melting. Okay, so typically AM described a professional production technique, which is clearly distinct, is different from conventional methods of material removal, which is we know is called subtractive manufacturing. So people may ask, what's the difference between the subtractive manufacturing and the additive manufacturing? Here's one to make a comparison. For example, if you want to make a 3D object, for subtractive manufacturing, you start with a raw block of the material, you machine down the parts you do not need, and then you create a 3D parts. But this is the waste material. For additive, basically you start with either powders or wire, and then you use a 3D printer and then build up a parts layer by layer, and then make a 3D part. And the amount of the waste is typically small. So you can see there's a big difference about the concept, how we manufacture a part. Okay, so towards to metals and for structural applications, conventional manufacturing method including molding, casting, forging, machining. For example, this is a typical process to fabricate engine block for automobile industry. And then so if you want to have a new design, you typically spend a lot of time and money for design the new molds. This is another conventional manufacturing process from forging, rolling, and then for the final part, you need to do a machining to gather the final product. However, for additive manufacturing, so you do not need this process, and then you just use a typical process, like you use a laser to melt the powder particles and then layer by layer, and then you can create a part without any molding and very simple post-machining process. Okay, so basically, 3D printing or additive manufacturing is not new. So the first printer was invented in 1980s, but mainly based on polymers. And there was a recent development and companies and build up polymer printers and metal printers. Particular from 2015, there's a big growth about the AM community. Let's take a look at the industry for additive manufacturing today. So you can see over the past few years, there's a big increase about the system sold for metal additive manufacturing printers. So you can see the total numbers increase quite a lot, and also the revenue increase. So the market is still growing. And then people may ask, where do we use for this metal additive manufacturing technique? So the major application field including aerospace, biomedical applications, some consumer devices, some application for defense, and also for some like motor vehicles. So we're going to talk about this in details. Okay, so let's talk about where we can use for metal additive manufacturing for industrial applications. First, we want to ask what could be the cost and the value analysis and the advantage and disadvantage of additive manufacturing method compared to conventional manufacturing method. So let's take a look at the cost. This is the manufacturing cost of per piece, and then the two curves showing one is the cost for additive manufacturing method, the other is for conventional manufacturing method. And then as a function of geometric complexity. This means when you have very complex parts for additive manufacturing, the cost will not increase, or the parts is not sensitive to complexity. However, for conventional manufacturing, if the part is very complex, the cost will be increased. Let me give you two examples. So you can see in the image in the picture A is a relatively simple parts. So the cost could be lower if you use a conventional manufacturing method. But for the parts in picture B showing very complex shape, and then the cost could be lower if you use additive manufacturing methods. Another analysis is about the cost per product as a function of how many units you want to produce. For additive manufacturing, basically, the cost is not very sensitive to the volume. And then, but for conventional manufacturing, the cost is very sensitive to the how many parts you make. Here's one to show you two examples. If you only want to make one or two parts or a few parts, additive manufacturing and is cost effective. But if you want to produce some parts for large volume production, like a Coke cans, then you need to invest a lot for the whole production line. And then for the high volume production for simple parts, the conventional manufacturing method shows advantage. So this can help you to decide in terms of cost whether or not you want to go for additive manufacturing or conventional manufacturing. And then I'm going to talk about what could be the advantage and where can we use for metal additive manufacturing. Okay, so the first is a rapid prototyping. If you have some idea and you really want to produce some parts and test whether or not the concept work, I think additive manufacturing could be a really cost and time effective way for the rapid prototyping. For example, this is a prototype of an engine block. This is a prototype of a motorcycle frame. Additive manufacturing can also help to produce parts with a very complex shape and geometries. For example, for this part, and so you can see this could be really difficult to make using conventional manufacturing method. Here's what, and just want to show you a few parts and made in our lab. So you can see this could be really difficult to make using conventional manufacturing method. Okay. Also, so you can see this part, there are some like internal cooling channels, and then so we can print it, the whole part, without molding machining. So you can see it shows very good surface quality and also with the internal cooling channel. For some parts, so you can see this is the head of a dinosaur model, and so you can see we can create a really complex shape. This is a lattice structure, and so you can see, and then so we can make a very small features. So for the method we use called selective laser melting, we can have the resolution about a few hundred micrometer. Okay, so since additive manufacturing provides the opportunity to make a complex shape and geometry, this can help us combine the topology optimization. For example, this is the original part, and then so you can see they show simple shape and design. The reason we use this chip is not necessary for this is not necessarily the ideal shape, but because this is easier for the conventional manufacturing. And then based on the topology optimization, so we found some parts, some material is not necessarily used. So this is the final parts. So we can see we can significantly reduce the weight of the parts, and meanwhile we can achieve the same or similar functions. This is two parts, and so we can make a comparison. So we can have about 50% of mass reduction. Okay, another big advantage is about a part consolidation. For example, this part traditionally is needed to made or from many different parts, and then you use drawing technology like welding, drawing, and to draw this part together. This is the same thing, but using additive manufacturing, so you can directly print this part without any drawing between this part. For example, here, so I can show you a parse, and so this is a parse. So you can see we do not need several different parts and drawing together, and then we can eliminate some residual stresses at the drawings area. And also a very famous example is GE lip fuse nozzle tip. So you can see this is a fuse nozzle tip used in GE engine, and then using additive manufacturing, they can made from original 20 parts to only 1 part, and then increase the durability, and then decrease the weight by 25%, and also increase the cost efficiency. So this could be a real good example how we can use additive manufacturing. Okay, so for the application, as I mentioned, additive manufacturing has been widely used for aerospace applications, from like a fuse nozzle, turbine blades, or for some structure applications in the aircrafts. And also we can use for the space applications. This is a very recent news. So you can see the SpaceX how the 3 different generations of their engine. So from very complex design and to a simpler design. And then, so in this process, additive manufacturing technique help to make a few parts together rather than you join different parts, make the design very complicated. Okay. Okay, so this is for the aerospace applications. Additive manufacturing has also a broad application for biomedical and health field, for example, particularly for implants. The main reason is additive manufacturing can make a part really customized. For example, different patients have different requirements in terms of their age and activities, and so using additive manufacturing methods, so you can make the parts customized to the patients. Another advantage is using additive manufacturing, so you can make some detailed structure like a porous lattice structure. This can help the bone to grow into the implants. Okay, so towards automobile applications, automobile industry is very sensitive to cost. So there's not a lot of direct, since additive manufacturing is still relatively expensive process. So there are not a lot of direct applicant like print the parts for cars and the trucks, but the additive has been broadly used for tooling application. For example, this is a insert for die casting. This is a internal cooling channels. So I showed you something like this, and then there are some internal cooling channels. So additive manufacturing has a unique advantage to create a complex cooling channel. So we call it conformal cooling channels. This is a conventional cooling channel. This is a conformal cooling channels. So you can see this is a temperature as a function of time, and the conformal cooling channels can provide a better cooling process, can make the temperature relatively stable and improve the production efficiency. Other applications including nuclear 3D printing part for the parts for nuclear reactor. This is the parts made by Oak Ridge National Lab in the US, and this part can be used for the nuclear reactors. Okay, and one more applications is additive manufacturing can also use for the jewelry industry. For example, we can use a laser to print the different parts and with a different geometry and customized design. So I think there's also future market in this field. Okay, so I talk about the where people can use additive manufacturing method for different applications. Now, for the next part, I also want to give a quick overview about metal AM techniques. Okay, so based on ASTM standard, there are 7 additive manufacturing techniques, including those for polymers, metals, and ceramics. For today's presentation, I'm going to mainly focus on 3 technologies. One is powder bed fusion. The other is we call direct energy deposition, and then the material jetting process. Okay, so the first technique we talk about is called selective laser melting or laser powder fusion. Basically, we use a laser and then goes to the scanning mirror, and then the laser goes to the powder bed and melt the powder, typically metal, ceramic. This can be also polymers. And then later, so we can create a 3D part. This is a EOS M100 3D printer in our lab. So this video shows we print the laser print the metals and the layer by layer. So we print the first layer, and then the recoater will have a new layer of the powder, and then the laser will melt the same part, the same area, and layer by layer we can create a big part. So you can see these parts and these parts, they're all made by this technique called selective laser melting, or people can also call it laser powder fusion. Okay, so in this process, and typically there are a few important parameters we need to optimize to control. For example, a key parameter is called the laser energy density, which is related to laser power, how much the laser power you use, and scanning velocity, hedge spacing is the distance between each layer, and also layer thickness. So we to make a good part with a high density, you really need to optimize these parameters and to make a relatively dense part. Another technique is very similar to the laser powder fusion, is called electron beam melting, or EBM. In this technique, we use also use a powder bed, but the energy source is different. Is using electron beam. It's very similar to scanning electron microscope, but the vacuum here, instead of using argon for laser powder fusion, we use a vacuum, and then the E-beam provide a faster scanning speed and a high power energy density, and also we can have the so we can have like a preheating powder bed. This is the part and made by EBM process, and so this is a technique is good for high volume production, for example, for drone implant and gas turbines. Okay, so I'm going to quickly talk about another technique we call the direct energy deposition. In our lab, we typically use a laser as the energy source. So basically, the laser and the powder goes to the same spot, and then the laser melted the powder, and then layer by layer, we can build up a large part. This is our in-house laser 3D laser DD system. So you can see we can use the laser to melt the metal powder and in the specific location and to make a parts. So initially, laser DED is a coating technique. We also call it laser cladding. So you can see we can use the laser to cladding new materials and will improve the surface performance. And then layer by layer, we can make a rather bigger part, and then for with a 3D structure. People may ask, what's the main difference between laser powder fusion and the DED? The main difference is DED can build up parts relatively faster and could be build up a larger volume, but the resolution, the spatial resolution, is not as good as laser powder fusion. Here, as I showed, and we can use it as repairing, and so you can see this is a part, and people can use the DED to repair the parts. Okay. Another big advantage for DED method is in the printing process, we can change material because there's a few nozzle. This is a very nice review paper and talk about make a compositional gradient material. For example, we can have alloy A and alloy B, and then there's a gradient between alloy A and alloy B, and then we can tune the composition and microstructure during this process. And then so this provides a good opportunity to design new materials. So based on DD and additive manufacturing process is not only make a part, but also make new material. Here, I want to show you a sample. For example, this part is made by DD, and the left side has a magnet made with a magnetic material, but the right side there's no magnetic. So we can have a gradient transaction from one alloy to another alloy. Okay, for DD, in terms of the energy source and feed material, so we have other technique. For example, we can either use a plasma or arc, and then the feeding material can be used as well. This is a wire arc additive manufacturing. The advantage for wire arc technology is that they have the building rate is much faster than laser powder filtration technique, and also the cost of wire is typically lower than powders. Another technique called electron beam additive manufacturing. Basically, the energy source is a electron beam, and then they use a wire to as a feeding material. So you can see they can make a really big part. The building rate is very fast, and but however sometimes the surface quality might be not ideal, and then sometimes the post machining process is needed to improve the quality of a finished surface. Okay, so I just talk about either laser or electron beam method. So this is a beam-based process, AM method. Now I'm going to briefly introduce a beamless AM method, mainly focus on binder jetting and cold spray. So different from laser based method, for the beamless method, there's no laser electron beam. So for example, this is a binder jetting process. This is very similar to conventional powder management method. So there's a loose powder and adding binder, and then form a green part, and then you remove the binder during the sintering process, and then for the sintering, so you can make the part even denser. Here I show you a sample made by this binder jetting method. So you can see the surface quality is also very good. The advantage of this method is there's no laser, and the system is relatively simple. The cost is relatively low, and also there's less safety concerns regarding lasers. The prostate of this part is relatively higher than some parts made by laser-based additive manufacturing. And for some part, it could be a problem, like for example, the fatigue property is really sensitive to process. But if this is a part not very critical for fatigue, and I think that could be also a good method to reduce the cost. Another method I want to mention is about the cold spray. Cold spray is based on the high pressure gas. The high pressure gas will accelerate the metal powder particle in the supersonic speed. and then layer by layer, they can form a coating. Here's want to show you a few parts. This is so you can see there's a different of a thickness. This is a aluminum powder particle deposit in substrate. This is a copper particle deposit on a steel substrate. Layer by layer, this is initially a coating technology, but we can also use it for additive manufacturing. This is a facility we located in NRC Boucherville, and they can use this method to deposit the powder. So you can see this is a copper powder deposited in a steel substrate. Okay, so also cold spray can be used for repairing. For example, this is the part has some surface pitting, and then you can use a cold spray for repairing. And also, there's a video showing about the cold spray technology. Okay, and also NASA also used the cold spray technology for their rocket engine parts. In our lab, we're mainly work on the microstructure evolution of this powder particle during the impact, and how this powder bonded, and then we try to work on different material alloy, how to improve the microstructure and mechanical properties. Okay, for the next part, so I want to quickly introduce about the project in our labs. So our research vision mainly focus on the material and manufacturing for the extreme environment. For example, the high temperature application, high speed impact, irradiation, corrosion, wire erosion, hydrogen embrittlement, and for complex loading conditions. So we want to integrate the material science research for additive manufacturing, and also use additive manufacturing to develop some new materials and structures. So we work on from processing conditions to characterization, microstructure analysis, mechanical testing, and then finally, we'll hope the material we produce can be used for different applications. Okay. And also want to introduce a few projects. The first project is about a metal powder. So no, the metal powder has been widely used for different technique. How do we select the best powders? Here is the metal powder we use in additive manufacturing technique. And then the metal powder needs to satisfy the powder size distribution, and also need to have good flow ability. In this project, we use computer vision method to quickly predict and identify the powder with good flow ability, good printing ability. This is the work collaborated with GE Additive. Also, we work on a project about the process optimization. For example, we print a part from 1D, 2D, and 3D, and then optimize the printing parameter like laser power, scanning speed, and to see how we can improve the print quality with less defect. Meanwhile, we're collaborating with a few labs identify the defect during the printing process. For example, we use a simulation AI aided simulation method to predict the keyhole depth. And also we work on in situ monitor. This is an in situ IR camera, so we can identify the temperature distribution during the printing process. Towards the material science, and we also use a additive manufacturing method to identify the special alloy for additive manufacturing. For example, we have a project about the high throughput alloy design using DED. During the printing process, we can control the feeding rate between 2 or 3 powder feeders and control their compositions. And then we can test the samples in different compositions and identify their performance, like wear oxidation, corrosion resistance, and also printability. And also we can use additive manufacturing method to control and design the microstructure. This project made on stainless steel, we can control the printing parameters and optimize the grain orientation and the texture. Towards the mechanical performance, and this project is mainly focused on the mechanical properties of aluminum alloy and high entropy alloy. This is a collaboration between my lab with the additive manufacturing team at Waterloo. So we did the tensor test of aluminum alloy, and then we characterized the process before tensor test and after tensor test to identify the failure mechanism. And also we work on additive manufacturing of a new alloy called high entropy alloy. They showed very interesting microstructure, and then we did a in situ tensor test in synchrone beam line to identify how the two faces deform during the deformation process. So the last topic is about like a fracture and the fatigue for titanium alloy. We mainly focus on the mechanical property and behavior. And then for there are two current new project. One is for additive manufacturing for critical mineral, mainly for permanent magnets. And another project is for small modular reactors. Okay, so for the future, I do see there's a great opportunity to include the AI in material discovery and additive manufacturing. So hope we can work on the additive manufacturing mechanics, the materials, and toward to a better engineering product for sustainable environments. Okay, so towards to the metal AM for metal application. So I think AM provide a good opportunity for industry 4.0. I'm looking forward to the bright future of additive manufacturing and in the new industry revolution.
Before we close, I would again like to thank Professor Yu Zou for being with us today. Thank you for delivering such an insightful presentation on the transformative potential of metal additive manufacturing. Your expertise and valuable perspectives obviously showed and are truly appreciated by our audience today. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. That's how we prepare for future presentations with input from previous attendees. A link to an online survey will be made available in the chat button at the bottom of your screen, and will also be shared with all of you after this event by email. Also, a link to the presentation will also be shared with anybody who registered in advance, whether you were online or not, all in the following weeks. Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. However, for the month of December, our next Skule Lunch and Learn event will be on Wednesday, December 4th. So please mark that in your calendar. Our guest speaker then will be Dr. Pratish Gawand, an esteemed U of T engineering alumnus, and is currently the CEO of Ardra Incorporated, and he will be discussing the transformative impacts of precision fermentation in sustainable food production and commercialization. So it will be interesting to see how that relates to engineering. In closing, I would like to thank all of you for having joined us today for today's presentation. With this, I hereby adjourn today's virtual event. May all of you have a wonderful rest of your day and your week, and we'll see you again next month on Wednesday, December 4th. Thank you and goodbye.